At this point in organic chemistry, you've learned so many reactions. And so the world is full of so many possibilities. What at first seemed like, oh, if you start with this specific functional group, you can turn it into this other specific functional group, which is how reactions seem when you first learn them in Organic Chemistry 1. And even as you start out in Organic Chemistry 2, now at the end of Organic Chemistry 2, the reactions should seem circular. You can turn anything into anything and turn it back again. Functional groups are indeed actual specific groups, but they're also potential groups. They have the potential to be turned into almost any other group. So you have sort of two parts to a molecule. You have the carbon chain, which we've learned a lot of ways to change, but that carbon chain determines what pockets the molecule can fit into. And then you have the functional groups, and the functional groups are really just reactive areas in a molecule. You could turn one functional group into another with a wave of a wand, or, if you prefer, just a matter of memory, with a drop in a flask. How about that? So when you see these molecules now, you see an ester, you see a carboxylic acid derivative. That's a previous chapter, but what we just learned with the malonic ester synthesis was if you have a carboxylic acid, you can make it from an alkyl halide. Now this is not a carboxylic acid, but isn't it really close? Can't you make that from a carboxylic acid? This carboxylic acid derivative? If we had, for example, this carboxylic acid here with 1, 2, 3, 4, 5 carbons and an OH there, all we'd have to do is do a nucleophilic acyl substitution. This is going to be our leaving group, and we'd have to bring in a nucleophile, namely ethanol. The ET is these two carbons there, OH, and you'd want to make sure that you use catalytic acid, and preferably you would remove water from the solution, so you'd heat it up so the water would evaporate. And by removing that product, you would shift equilibrium to the right using Le Chatelier's principle and increase your yields of this. Now you drew the mechanism for this in a previous chapter. You drew the mechanism for the hydrolysis of esters. This is really just the reverse of that. You're forming the ester by adding an alcohol and a carboxylic acid. So that when you see this carboxylic acid derivative, you would want in your mind to make a conceptual connection to a carboxylic acid itself. And once you have a carboxylic acid, well, then you can make a connection to the malonic ester synthesis so that you could use the recipe that we had above here. Now I'm going to take it from the notes we have from the video where we introduced this for the first time. So this is our generic recipe for doing this malonic ester synthesis. So once you have a carboxylic acid, you would say to yourself, I can make that using the malonic ester synthesis. All I would need is diethyl malonate, and indeed, in the prompt for this exercise, they said, starting with diethyl malonate. So we knew we had to use the malonic ester synthesis anyway, but that would be a hint that you want to think back to the carboxylic acid that you can make this from, because that's what you make in the malonic ester synthesis. Propose an efficient synthesis. Okay, well, all we need, because if we have this carboxylic acid, we could use this recipe to get our ester here, this ethyl pentanoate. All we would need is to know what alkyl halide we would have to add to the diethyl malonate. Well, when you do the malonic ester synthesis, you add 2 carbons with a carboxylic acid at the end of that chain. So when you look at your carboxylic acid, you're trying to think, what alkyl halide should I have? Take the carboxylic acid and the alpha carbon next to it and erase it. So I'm going to take this molecule. Now we're working backwards, we're doing retrosynthesis, but I'm going to take those pieces and I'm going to erase them. Those are going to come from the diethyl malonate, not from the alkyl halide. So we have this here. And where those two carbons were, oops, sorry, wait a second. So you want to erase that whole thing. Where those two carbons were, you would draw in a leaving group. So I'm going to put bromine here. It could be any leaving group, chlorine, iodine, whatever. And that is your alkyl halide. That is the carbon chain that you would want to add in this for this Rx. So we can sort of take this and have that as our alkyl halide. And so we could replace that R group with these three carbons. So 1, 2, 3. And that would give us this pentanoic acid. And once we have pentanoic acid, we just do this nucleophilic acyl substitution. We add ethanol and an acid catalyst, remove some water, and you create the ester from the carboxylic acid. So overall, you would start with diethyl malonate. That would be your original reagent. And then, first you would treat this with sodium ethoxide in ethanol solvent, and that will steal the alpha hydrogen here, turn that into a nucleophile. Then you'll do an SN2 reaction with that nucleophile using the alkyl halide we saw. That attaches the carbon onto that alpha, the new carbon chain onto that alpha carbon. Then you use aqueous acid to hydrolyze the esters, turn them into carboxylic acids, and heat to decarboxylate it. So a carboxylic acid comes off, and you just add the two carbons in the carboxylic acid group. Now that would give us, that malonic ester synthesis would give us the carboxylic acid that we need. And once we have the carboxylic acid, we can turn it into this ester by adding the new nucleophile to do a nucleophilic acyl substitution. And so our nucleophile here is just this group that replaces the OH, so an ethyl group with an oxygen, but we have a hydrogen on it to stabilize it. Make sure that you use an acid catalyst, and to improve the efficiency of the reaction, use Le Chatelier's principle, remove product, water, and that'll shift equilibrium to the right and make you produce more product. So that overall, if you use this recipe here, you would create that beautiful work of art there. So you could really start with 1 bromopropane, and if you mix it with all this stuff, you'll turn it into this ester, ethyl pentanoate. Okay, let's try that same procedure with a different molecule. And again, note what's happening here as you approach the end of this class. Functional groups can almost all be turned into each other. It doesn't matter what the specific functional group is, you can turn it into almost any other functional group. So we have so they just turn into really reactive parts of the molecule. We have an alcohol here, but if they're asking us to make this molecule using diethyl malonate, well then we need to use the recipe, the standard recipe for malonic ester synthesis. So I'll take that recipe from that previous video, and the thing with this is, though, that this malonic ester synthesis makes carboxylic acids, and that's not what we have here. But what we know now is that almost all functional groups can be turned into each other. So maybe after we get this carboxylic acid, we can turn it in to the alcohol that's here. So let's try it. Maybe, what carboxylic acid would we have to turn it into that? Well, we would want the same number of carbons, same type of carbons. We would just want the carboxylic acid where the alcohol is, at the end of that 3-carbon chain. And when you do the malonic ester synthesis, you add the carboxylic acid and the alpha carbon there, carboxylic acid and the alpha carbon. So if you wanted to know what alkyl halide to use, you would take that and erase the carboxylic acid and the alpha carbon. And where the alpha carbon was, you would write in a leaving group. I'm going to use iodine. It could be any leaving group. And so that is the R group in this alkyl halide. So we can take that molecule and replace the alkyl halide with it. That will replace this R group here with the carbon chain we have. And you'll notice that that carboxylic acid is the one that we wanted earlier. So if you take diethyl malonate, you rip the alpha hydrogen off with a base, sodium methoxide and ethanol, and then you do an SN2 reaction with an alkyl halide, with this alkyl halide followed by acid-catalyzed hydrolysis of the ester and heat to do the decarboxylation. You'll end up with this carboxylic acid. Now, once you have that carboxylic acid, how do you turn the carboxylic acid into an alcohol? Well, you'll notice what we have here are 3 bonds to oxygen, and here we only have 1. In other words, we've reduced the number of bonds to oxygen. In other words, we've done a reduction. So you can use a strong reducing agent like lithium aluminum hydride. And just remember, whenever you use lithium aluminum hydride, to follow it up with a water wash to stabilize any charges you make by doing proton transfers. So overall, if you start with diethyl malonate, that's 3 carbons with ethyl esters on the ends. If you start with diethyl malonate and you do the malonic ester synthesis, so first treat it with sodium methoxide in ethanol solvent, and that rips off the alpha hydrogen here, turns that alpha carbon into a nucleophile, and then do an SN2 reaction with an alkyl halide that gives you the right carbon chain. And then treat it with aqueous acid, hydronium, to hydrolyze the esters so that they become carboxylic acids, followed by heat, which decarboxylates one of those groups, so you end up adding 2 carbons and what is ultimately a carboxylic acid after the hydrolysis. That gives you this carboxylic acid here. Once you have that, you just want to turn it into a primary alcohol, so you do reduction. You treat it with a strong reducing agent like lithium aluminum hydride, followed by water just to stabilize any charges with a proton transfer. And so overall, if you used this recipe, it would create that work of art right there. And molecules like this are not insignificant. This is not just a random structure. If you look up the structures, for example, for dopamine or serotonin, for adrenaline, you'll see structures very similar to this. And so these recipes are not just building castles in the air. They're building castles in your body that you can use to change people's lives. Okay, let's do this one more of these multi-step syntheses with the malonic ester synthesis. Now, we know they told us in the prompt that we have to start with diethyl malonate, but let's say they didn't. Let's say we're just trying to creatively apply what we learned in the last couple of videos. What you'd see in this molecule, what you should see now are conceptual units. I mean, sure, you want to be able to see specific structures, but you are a magician now. You can change anything you want in these molecules. So what you want to see is potential in addition to just actual things. And you'll see this carbon chain. That's going to tell you what pockets this molecule can fit into, so shape. And then you'll see this functional group. And when you see a functional group, you want to see every functional group there. Now, obviously, you want to see what specific functional group it is, but you can turn that functional group into anything, any other functional group. Functional groups are just transformative areas of molecules. Now, what we have here is an amide, carbon double bonded to oxygen, single bonded to an amine, and that's a carboxylic acid derivative. So any carboxylic acid derivative you can ultimately make, it might take a couple steps, but you can ultimately make from well, you can ultimately make from a carboxylic acid. They are, after all, called carboxylic acid derivatives because you can make them from carboxylic acids. Okay, so if you replace that amide with an OH, that would be a sort of carboxylic acid that you could turn into this somehow. We'll worry about that detail later. Once you have this carboxylic acid, well, then you can say, I can make that from a malonic ester synthesis. All I need is an alkyl halide. So we'll go back, get that recipe for the standard recipe for the malonic ester synthesis that we learned in the video where we introduced it. And to make that carboxylic acid, we just have to figure out what alkyl halide we have to add. And when you're doing that, remember that the malonic ester synthesis adds 2 carbons and the carboxylic acid. So look at your original molecule, look at the carboxylic acid and the carbon next to it. Those are both going to be added from diethyl malonate. So what's going to come from the alkyl halide? Everything that's left. Take that same molecule, redraw it, but erase what's going to be added from diethyl malonate, and you have what needs to be added from the alkyl halide. So you can draw in some leaving group, fluorine, chlorine, well, chlorine, bromine, iodine, those would work. Fluorine isn't a good leaving group because it's so small, so it can't stabilize any negative charge it has over a big area. You can't dilute the charge. So chlorine, bromine, iodine. Well, that's our R group there. So we can take this and use that as our alkyl halide in this SN2 reaction. And so, this R group is what we can use to replace this R here, and we'd end up making that carboxylic acid. And that was the carboxylic acid we wanted to make up here. That was the sort of derivative of this amide. So you see the functional group, you think, I can make that from a carboxylic acid, and I can make a carboxylic acid from an alkyl halide and diethyl malonate using the malonic ester synthesis. Okay, well that's how we can make this carboxylic acid. But how do we turn that into the amide? I mean, it's one thing to say, well, I'm a magician now, all I have to do is wave a wand. It's another thing to remember the specific reagents. Now, it is a nucleophilic acyl substitution. So you are going to take this leaving group and replace it with a nucleophile. The problem is your nucleophile can't be NH3 to begin with, because NH3, ammonia, the nitrogen version of water, is a base, and it would just react with this acidic hydrogen. It would steal that as a base. So you can't react with it yet. You have to turn the carboxylic acid into a molecule that is not acidic, and preferably more reactive to improve the efficiency of the reaction, because ammonia isn't the best nucleophile. Well, the most reactive carboxylic acid derivative are acid halides. So we could turn the carboxylic acid into an acid halide by adding thionyl chloride. Once you have thionyl chloride, then you can treat it with excess ammonia to turn the acid chloride into the amide. So altogether, we started with diethyl malonate. Three carbons and ethyl esters on each side. We ripped the alpha hydrogen off of that using sodium ethoxide in an ethanol solvent. Then, once the hydrogen was ripped off and that alpha carbon was a nucleophile, we did an SN2 reaction with an alkyl halide. We designed the alkyl halide to give us the carboxylic acid that we want. You did that SN2 reaction, then we add some aqueous acid, so some hydronium, acid in water, that hydrolyze the esters, turns them into carboxylic acids, and then you add heat that decarboxylates one of these molecules. It takes one of the carboxylic acid groups off as carbon dioxide. So you only have one left. You added 2 carbons and the carboxylic acid group. Okay, so that gave us the carboxylic acid we want. Then we just needed to turn it into an amide. We couldn't do that directly because ammonia is a base and carboxylic acids are, of course, acids. So that would do a neutralization reaction rather than the nucleophilic acyl substitution that we want. So first we turned the carboxylic acid into something that's not acidic and even more reactive. We used thionyl chloride to turn it into an acid chloride. Once we had the acid chloride, well, then we can use a weak to moderate nucleophile like ammonia to replace this awesome leaving group, chlorine, with the incoming nucleophile ammonia. And you use excess so that the second equivalent can steal hydrogen from the first one to make it NH2. So, if you followed this recipe, you go into a laboratory late at night, thunder in the background, laughing, and you mix all these things together in this order, then this Frankenstein molecule would pop out of your beaker cauldron. And so, hopefully this video gives you a sense of how exciting and beautiful and how much potential there is in the malonic ester synthesis, and how it connects to all of the reactions you've learned so far, and how now every molecule you see, you don't just want to see what it is, you want to see what it could be. Kind of like if you're generous, you would do with the people around you. You don't see them just as what they are, but as what they could be. And so you help to transform them that way, at least with these molecules, with all the reactions you've built up over the course of your career in organic chemistry.